All right.
Got
Hi,
it.
everybody. Thank you so much for coming. I'm just going to quickly introduce our speaker today. Our speaker is Professor Gheshnizjanni. She's a faculty member at the Perimeter Institute for Theoretical Physics and an adjunct professor at the Department of Applied Mathematics at the University of Waterloo. She's also associate faculty at the Waterloo Center for Astrophysics. She got her PhD from Department of Physics at Brown University and the postdoctoral position at the University of Wisconsin-Madison and the Perimeter Institute and University of Buffalo. She's a cosmologist and studies topics like early universe, the cosmological Big Bang, and some topics in late universe, such as dark energy models. We are super excited to have you. Everybody is really, really looking forward to your talk. And please take it away. You can introduce yourself if you want in a different way, or you can just jump into your talk and everybody can raise their question if they have any questions. Okay, please take it away.
Sounds good. Thank you, Azadeh, for such a
Yeah.
nice introduction. Let me start by sharing my screen.
I mean, I have to make you a
Oh,
host.
oh yeah, yeah. Does that?
Yeah, go ahead. You should be able to share a screen now.
Okay. One more step.
There you go.
Okay. And bring back my own window so I can see you all. Okay. So I'm very excited to have you all here. It's not every day that I see many enthusiastic children and young adults who, I mean, there are a lot of people who like to know about Cosmos, but to really seriously come to a talk and sit through it, that's quite commendable. So thank you for coming. Hopefully you all take something out of this talk. Again, it's not meant to be like a lecture. If you like to interrupt me, if there is a question, if I know the answer, then I try to explain and we can talk talk about it together. Let me see if my cursor works. Yes, yeah. Just to give you a little bit of orientation, I am in Canada. I live in a city called Waterloo, which is in Ontario. It's not that far actually from Toledo, Ohio, maybe a few hours drive. And the place that I work in is in this building, which is the Perimeter Institute for Theoretical Physics. And the name of the perimeter itself apparently was because the person who founded the institute wanted for people who are working on the perimeter of the science, the edges of the knowledge, to gather there and do theoretical research. To be a little bit more specific, to give you an idea of what I do personally, and for this young audience, I don't think you have ever seen the phones with the wires. But back in the day when we wanted to talk on the phone with someone, the phones used to look like this. So this image is kind of showing you me talking to different kind of scientists and trying to put it together. Sometimes I call I call myself like I am a space detector or inspector. So you, on one hand, you have the data that come from space. Again, it used to be that telescopes would look like this. Nowadays, you have big satellites over the sky. You have ground-based detectors deep in the ground who are getting the data from the space. So it's much more sophisticated. And on the other hand, you have some mathematical tools. Or in other words, I always like to say, mathematics is the language of science. You know how to express your thoughts in that language. So it's a kind of like a wrench that we use. And the fundamental laws of nature are expressed in that language. So we try to put them together, the data and the math, in order to make sense of what happened in our cosmos, and the cosmos or our universe, as far as we can go in the past, in the future, as large as it can be. And to give you a little bit of a picture of what I'm talking about, because sometimes I get questions about solar system or things that I'm not much of an expert on, but I like this picture that's, we start from the Earth and then we kind of go to space. If you go further out, zoom out, you see the solar system. Of course, this picture is not up to a scale. Sun is much, much bigger than Earth, but you get what I'm getting at. And then you zoom out and go further out, you see the universe at larger scale, where sun is just a dot in the galaxy, Milky Way. And if you zoom out even further out, you see a bunch of galaxies, and you keep doing that. And then like billions of galaxies start to emerge. If I was this supernatural being that could view that, then I would be kind of like looking at a big box or a big space, time, everything there. But of course, we are sitting at Earth and making all these observations from different or in different angles and try to put that picture together. And interesting enough, as you zoom out and zoom out, eventually, even those big galaxies all will become dots in that image. And in this very zoom out, a very nice pattern emerges, which we call cosmic web. It's kind of like a spider web in a way. And these are all the matter or visible matter that exists in universe and are observable to us. Now, looking at this picture, this is basically kind of what dictates how the matter in the universe is distributed and what the cosmos is doing on those scales. So that's kind of the distances that I work with, or like the kind of physics that I'm looking at, like what happened at that very big scales and what would happen if you now turn the tape backwards in time and see what happened in the beginning, because everything is somewhere in the universe within these dots, but how they formed and how like the galaxies became to exist, and they all happen in these things, and it has to do with this formation is imprinted in this picture. Okay, does that sound good? Does that make sense?
Any questions so far?
And if you want to know what, and again, I'm not very good with numbers, but if you want to get a sense of the scales, like the Earth is about 10,000 kilometers. And then when I'm looking at this picture, this is like 10 to the power of 23 kilometers. So way, way, way larger distances here. Something you may notice in this picture also that it's very fuzzy. So when you're looking zoom out to this at this distribution of objects in the universe, it's almost kind of uniformly distributed, which makes it much easier for us to handle mathematically. But there is also a lot of information in these small patterns, like why there is more matter here, more galaxies are stuck here, but why there are these voids and empty spaces there. So in fact, this is extremely helpful for us to decide what happened at the beginning of the universe. So what kind of processes or physics was happening back then. So people used satellites to map up the statistics of the distribution in order to test our theories, mathematical theories and laws of physics. Also, to give you again the idea of what numbers we're working here. So like a Milky Way is just one galaxy out of the estimate that we have in the observable universe of 100 billions of galaxies. And to put it in perspective, like if you counted the number of stars, it would be within this 100 billion galaxies, it would be almost the same number as all the sand in all the beach is on the Earth. So that's how much like matter we have observed in the universe, or we know they exist at least. And in a way, it kind of makes us humble. Like, you know, we think we are very important on Earth, sitting on this very dot, but there is like, and our sun is really obviously very important to us, but there is so much more of it in the universe.
The picture that you showed on the previous page, the background, the blue background that you had, go one back more.
Oh yeah.
The picture, this background over here. What is that, visible light?
This is the visible white. Yeah.
Oh wow. Okay. So where are we looking at? This is a small space, like a small region of space that looks like this.
Yes, this would be, and actually this is the artistic
Okay.
view, but at the end of the talk, I have one that is actually from the observations, and
Okay.
if you want, yeah, can jump ahead to the, that's
No,
my
that's
very
okay. I've never
yeah,
seen
but
a picture like this. That's why I was like, where is it? Where are we looking at? And why does it look like that?
Yeah, this is most probably a simulation image, but yeah, the actual one actually does look a lot like this, and you see this kind of filament shapes, or like the in the galaxies are clumped up in this very light regions. But there is more to the story actually, as I will hopefully get a little bit into it. Like most of the things that we think exist in the universe are not the things that we see, so that's another important part of it.
All right. Yeah. Thank you. Yeah.
No problem. Yeah, so what kind of physics do I deal with in describing this picture, what's happening in cosmos, how things are moving or like shaping? The governing or the most
question. Sorry, there is a question. Jack has a question. I just haven't scanned the room yet, but Jack, do you want to go and ask your question?
Yeah, go ahead.
Jack, do you want to ask your question? Your hand was up.
Maybe it was the AI.
Maybe we can move ahead, and then if there is a question, we can come back. Yeah, go ahead. Sorry.
That's good. Yeah, so the physics that is most important on this kind of scales is the force that is the most important character in the story happens to be gravity. Now, many of you, I know you're at different grades, so you probably have been introduced to different forces at this point and with different technicality, but probably most of you have heard about different forces of nature. There is like a magnetic force, there's electric force, and so on. But the most
magnetism, electromagnetism.
There you go.
Gravity.
Yeah. Anything
friction.
Else? There we go. So now, the most important one for our story is gravity. And for gravity, how much understanding we have was most of it early on, 300 years ago, was developed to what we call Newtonian physics or Newtonian gravity, which you probably have heard the story of the apple falling and then Newton. I don't know how historically accurate that the story is, but then he writes his famous force of gravity, where Earth pulls out objects towards its center, anything that has mass. So, and we all know and love it. The Newtonian physics or description of gravity works very nicely on Earth. No matter where on Earth we are, in Australia or in North America or in Africa, you know, everything you drop something, it goes back to Earth. The plane,
however, Isaac Newton actually didn't get hit in the head with an apple. He actually he learned that gravity worked through years of full calculations.
Oh, that's very good point. I really appreciate that, because I wanted to make that point later on about Einstein, that it's not that you wake up one day and you figure out the laws of physics. You have to really work hard for it to formulate
if just wake up one day, you discover the laws of physics were how it worked, then
no. Yeah.
I like if it it works that way, everyone would be a scientific genius, and most people are not.
And
Thus,
I don't think there
obviously
is
doesn't
such a
work.
thing as a scientist genius. I think every scientist, even Einstein, as I will tell you, had to work really hard to formulate the laws or find them.
Yes,
Steve, you have a
however, what
question?
had
Yeah,
said is
let's give Sid a chance to talk also. Sid, go ahead.
Actually, I think Newton didn't discover gravity.
Oh, who did?
Actually, Indian people discovered it way before.
I wouldn't be surprised because there was a lot of science that was developed even before Newton in a lot of other countries too. It's just that maybe people like not everybody was aware of it. That is true.
Yeah,
Yeah,
So
August, go ahead.
my
August,
dad told me.
Mhm.
Yeah, that's good. Do you know who
Okay.
that was? What did your dad say? Who was the person who discovered gravity?
I didn't. I don't remember, but
Okay.
Mm.
Yeah, I wouldn't be surprised either. August, go ahead.
Hmm?
Oh, I think we maybe we lost.
Lost him?
Yeah.
Okay. So, but my point here is that turns out the Newtonian description of gravity, the forces, was very nice. They work for us on Earth. But once things get like we go to space or in certain very high energy system, it doesn't quite work that way. And in fact, it's not just gravity. The other forces, the same thing happen. In fact, it turns out the whole describing how things move or pulled based on forces, it started to change that idea in the 20th century because there was another way to understand all of this, which was much more powerful, which is a story for another time, like waves and fields and all of that. But in this case of gravity itself, there was one guy who started notice some things are not quite, or some things are very strange in gravity. Like how, for example, the mass seems to have these double agents roles in the formula or other things. So, or the speed of light, for example, seem to be special. And so let me see. Yeah, I wanted to say, yeah, so maybe I point this out before moving to that story, which is like in the story of Newton gravity, things are kind of pulled out with the force. Like you have Earth that pulls the moon, so that as the moon is rotating, it cannot get away, it rotates around it. And the sun is pulling the Earth, and then therefore Earth cannot just get away, it just goes over the, so it's kind of, you have like the forces act as like somebody, you're holding someone's hand when they're spinning, you hold them together, it's kind of like a hand pulling and pushing. But now the next story that emerged, thanks to partially this guy, August, you're back, you have a question. Go ahead.
So then, would if the moon is pulling towards the Earth, wouldn't that mean there's slightly less gravity during when the moon is directly above you? And there would be even more gravity during solar eclipses.
It depends on when on Earth you are, I assume, because the places are that like on facing the moon, obviously they're closer to the moon, they're pulled more than the places that are behind the Earth or like on the other side. So that's one thing. But the eclipse, would that matter? I cannot think why it would matter if there's eclipse or not.
Well,
Yeah.
I'm saying like the eclipse would because like both the sun and the moon are like
Oh, I see. In the old picture, you're saying, well, this one is pulling, but someone cuts through. Yeah, well, I want to say that picture is not actually quite that accurate. But no, these are invisible hands. They can go through each other. So it is, even if the moon is in front of the sun is still pulling the earth.
what I mean is
Yeah.
like the moon from the sun, that means the sun is tugging on the earth and the moon is tugging on the earth at the same time.
Yeah, exactly. Oh, I see your point. Yeah, then they're both pulling it towards the sun,
Yeah, so they're pulling
towards that center. Yeah.
there should be slightly less gravity on that spot, on the earth.
Yeah. Yeah, that's true. And that would have a effect on it.
The
Very
decrease in
smart.
gravity would not be noticeable at all, though. It would be too small.
What's that?
The decrease in gravity would be impossible to
Mm.
notice because the moon does not exert much of a gravitational force on an observer standing on the Earth.
Well, just maybe not for an observer, but have you, and again, let's not get too much distracted, but maybe we have to look at the tides, right? Because the tides are because of the moon and how moving is pulling the waters towards itself or away. So let's get back to our story and Mr. Einstein. So what happened there? So he came up with a new way of thinking about the gravity. And the way he thought about, first of all, there was a major discovery before so there is two contributions from Einstein to gravity. One is the special relativity, and then his major contribution, the theory of general relativity. And the special relativity came first, which kind of started to hint that we used to think like we live in 3 dimensions. You know, if you have done, like we have the x direction, the height or the width, and so like that. And then we have time, which we measure with clock. But Einstein in special relativity started to see, well, the time is kind of like another dimension. So we should put them together. It's like we have 4 dimensions. One is a little bit special compared to the other one. And therefore we have this geometry, and this is where the geometry and math comes in, where you have a 3 + 1 dimension. You have to think of it as a space-time, and everything is imprinted in space-time geometry, and gravity has to do with that. Now, before I complete that, Torin, you have a question?
I agree with Sid when he said
Okay.
Isaac
good.
Newton didn't discover gravity because
Okay.
he's wasn't he the person who made the laws of cooling?
The laws of cooling. He did have a lot of work in physics, but I have a suggestion for you. This is gonna be homework for you all, to go and figure out historically who came up with the theory of gravity first. How is that? Okay. And then you have to do a research, and your research needs to have some evidence. You have to have that. Okay. That's kind of exercise to be a scientist. So now,
But I don't like homework. I really don't.
I know nobody does, but yeah, think of it as a fun activity. How is that?
Sure.
Hold on, Rex has a question too. Rex, can you go ahead and ask your question?
I like homework.
Oh,
There
okay.
you go. That's, yeah. I think of a homework. I don't think of it as homework. Maybe homework has a bad rap. Just think of it as a fun activity.
Research project.
Yeah, exactly.
Hey, Max, if you like homework, how about you do mine for me? Huh? That'll make you happy, and it'll make me happy, right? Because if you like homework.
Okay.
So
let's,
August
guys.
has a question. Let's just ask, let's see what August has to say, and then we gotta let you go forward a little bit.
Yeah, because we want to get to the beginning of the universe. And
yeah, exactly.
Let's
do one August and one Sid quickly.
So
go ahead.
So something there's something strange that happens when you put Einstein's math. That basically astronomers are trying to find out what happens when a star dies and collapses in on itself. Basically, it carries to a black hole. But at that time, they were they found a bunch of things. Electron that they thought would stop it. Electron degeneracy pressure. Neutron degeneracy pressure, which makes the different weight dwarfs, that kind of stuff, You know,
Mhm.
and
It's
yeah,
very cool. And in fact, it's very important that we understand them very well because even in us cosmology, those things have applications.
they were like,
Okay.
so wanting to like, they just didn't like the idea of having that, of like having a
Mhm. Yeah, no, yeah, that's a very good point. I was just 2 weeks ago in a conference called Black Holes Inside Out. And believe me, there's a lot we still don't understand about them and how they're formed. Sid, you have a question?
well,
August, let's sit talk, and then we're gonna ask after that to
and
just
Mom,
move on a
stop.
little bit. Okay, Sid, go ahead.
I like homework.
Okay, all right.
There we
So
go.
let's let Dr. Ghazal speak a little bit more because we want to get to the cool stuff, right? You guys want to hear the
Yeah,
whole story,
yeah,
right? Okay,
sure, yeah,
let's
yeah.
hear more.
So, right. So the picture I have in front of you is not very accurate because it only has this geometry or these lines which are going in towards the center and radially or angularly. But think of it as a space-time now has 3 dimensions in space and 1 dimension time. So this is something that our brain may not be able to picture. But Einstein came up with that idea that if we have the geometry of that, and it has its own fabric, the gravity can be explained through the geometry of that fabric, so fabric of a space-time. And so the way that it works, it's not that sun is pulling Earth anymore, for example. Sun has a big mass. It curves the space-time, so it gets curved up. And that curvature also, like the whole fabric gets curved up. And so does the Earth, every object that has a mass. And this curvature makes things because to move in a certain, now, like if Earth has to move, for example, in the orbit because of this is dictated through the curvature of the space-time and the fabric. It's not that it's directly being pulled out from the sun. And it has implications because, for example, it means for things that happen in the center in here at sun, if I like, for example, sun vanishes tomorrow, it's not going to be that right away Earth will feel it. It will take time for the curvature to move into like a wave of curvature or space-time deformity to get to Earth, and then Earth would know, and then something would happen to its orbit and it would move away. So this has all interesting impact. And in this way, so he wrote his equations. And in fact, I like the story there because it took him about 10 years to come up with the right formula and equations. He didn't, because part of it was because he didn't have the right mathematics, and then some of his mathematician friends pointed him to some work that had been done by some other mathematician like 50 years before called Riemann, who for some interesting reason, and that's why I'm like, sometimes people do things that like work on mathematics and you think, oh wow, they're wasting their time. Why is it that interesting? You never know, like sometime later, someone has come in and turns out it was a very nice mathematics that they needed to come up with their theory. And in this case, Einstein was lucky because Riemann, for example, had written the differential geometry, how to describe geometry of higher dimensional spaces. And in fact, I think he gave it few tries and made mistakes until he finally wrote the equations that seemed to work out. And he predicted few things. For example, like one is that the light would get bent if it moves in the space-time, because now it's not about the force anymore, it's about the geometry. And then like the perihelium of Mercury would, there was a certain impact on that. And in that case, again, remember my phone call? The astronomers went and measured those effects, and that was the evidence that the theory was actually correct. The Newtonian theory needed correction, and the Einstein theory works better when you go to these largest distances. So now, what does it have to do with cosmology? because on the large distances that I work on, same story applies. I told you there is matter that is distributed in the whole cosmos. So how it's distributed will tell me how the fabric of universe, the geometry would look like. And this has to be a consistent picture. And we have to make sure it works out. And in fact, there's a very funny story there, which is that Einstein and other physicists at the time tried to do that, say, okay, if this is the correct theory, it should also work at large distances. Let's put it together, see what would happen to the cosmos on those distances. But what they realized was that it wasn't quite working, because if all the galaxies and stars are distributed, like think of it on this image, the geometry would be such that they all should be getting closer and closer to each other. Like if I take a piece of the space, it should get shrink, or it should be expanded. You cannot just hold the galaxies in their location like in a static way. It just wouldn't work. It's kind of like if you put a ball on the side of a hill. So obviously it's not gonna stay there. It's gonna either go this way. I mean, obviously it's gonna fall in this case because you have Earth here, but it cannot stand there. So Einstein realized, oh, there's something wrong with his equation. Something's not working. So he tried to manipulate his equations, and that's sometimes some people do, like, you know the answer of the homework or the question, it doesn't come up quite right, then you try to, maybe I made a mistake, maybe I missed something. And in this case, Einstein thought he missed the constant. So he added by hand the constant, to his formula, some constant number, and said, well, if there's a constant and its value to be determined, then I can make it work. I can make this picture to hold it statically, nothing moving. The galaxies are pinned in this image, they are not getting away from each other or collapsing into each other. So that would work. But then soon they realized even that doesn't quite work, because it might work for one instant or very small amount of time, but it's like putting a ball on the top of the hill. A little bit of a wind would move it in either right or left, and it would make it fall down. So how could be, like, we had the universe for years and billions of whatever ages, and it's still holding itself together? That still doesn't work. That's not a good way of explaining it. Anybody knows what happened to that? What was going on? Any guesses? If you cannot hold everything statically, all the galaxies, what could be the cause, or what would be the problem? Yes, Pierce.
Everything's getting further away from each other?
Exactly. Einstein didn't know that. He thought the galaxies are sitting there not moving. But then here comes this guy, Hubble, and he was making astronomical observation, measuring distances in the universe, and how things are, this velocity of the galaxies and so on. And then he realized, well, looks like the things that are further away from Milky Way, they're getting away from Milky Way faster and faster. They're not standing there. The galaxies are getting away from us. And then again, this peculiarity is not just getting away. Something that is further from us is getting away from us faster. And this is called the Hubble law. So something must be happening. What is that?
Lauren, that's Lauren. Lauren, go ahead.
Lauren, go ahead.
Is it true that Einstein added the cosmological constant because he didn't like the idea that the universe was expanding?
I think he just didn't know.
But you
could be right.
I feel like he really didn't like that idea.
Yeah, I think people didn't even comprehend the fact that the whole universe could be expanding and that fast at the time. It was just something, I mean, first of all, think of it. If Hubble himself was among the first people who noticed there are things outside Milky Way. So the amount of progress that was made during those years was quite amazing. Like we went from thinking everybody is in Milky Way into, well, there's actually way more stuff outside of Milky Way. And then wait, not only that, there are these galaxies, these things that are getting away from us very quickly. August?
Okay, so okay, maybe the great attractor thing is moving away. Or there could be strange, like, actually, never mind. Yeah, maybe the great attractor is moving. You know, that thing that attracts everything? Everything to it?
They're all moving, yeah, more or less.
Mhm.
And on average, yeah. And so there's a very easy way to understand why the things that are further away are getting away faster. And I like this picture, which is from this book, actually, by the way, is Barbara Wright, and we often use it in university to teach cosmology. So think of it like if you have you're baking some raisin cookie or cake, and you have the dough, and you put the raisins in the dough, and let's say assume it's like a rectangular cube, and then you put it in the oven, it's going to expand. So it's going to expand in all directions. But if you're sitting on one of these raisins, and let's say raisin 1 is 1 centimeter away, the second one is 2, and the third, after it expands for like 1 hour, raisin 1, the whole thing has expanded. Raisin 1 is, the distance between raisins have now gone from 1 to 3, but the raisin 1 has got away from you 2 centimeters, but the 2 has got away from you, has gone from 2 to 4, and third has got away more than the other one. In 1 hour, the third has got, relative to you, has got away 6 centimeters away from you. So it looks to you, it seems like, wait, this is going faster versus this one. And so 1 is a slower, 2 is faster, and third is the quickest of all because it's further away. But in reality, it's just that the dough is expanding. So if you put that picture together, the same thing was happening in the universe. Everybody was getting away from everybody because the whole dough was expanding, the whole cosmos was expanding, and then the law was perfectly explaining that. So that was a major discovery. And therefore, going back to Einstein, it's like, oops, what did I do? I made a mistake. I have to just take it away. I didn't have to manipulate the formula. It was just working fine. Leave it as that. Now, there is an interesting twist to this story, which is back in when I was in graduate school, about like 2000 or so, there were new discoveries starting to emerge, new data in astrophysics that showed that not only the universe is expanding, it's actually the expansion is getting faster and faster. So it's as opposed to if you had regular matter or radiation, it would slow down. Even if it was expanding, you would expect it to slow down. It's getting faster. And again, the only way you can explain that is by bringing back the constant. So it could be that Einstein wasn't wrong after all, and maybe it was, again, like now you have to bring it back to explain it. We don't know yet, so there's a lot of investment in science and scientists working to resolve that acceleration of the expansion, and that again would be an interesting story by itself. Now, I also like to point out, you do hear a lot about the men who contributed to physics in the history, but I do like to bring up 2 prominent women who, despite all the challenges that women faced back in the day to study physics and do physics, did a lot of contribution to the story of gravity and cosmology. And one is Amy Noether, who was a mathematician, but she was so smart, and this was like her side project, who just looked into Einstein's theory of gravity and figure out certain symmetries and how to define masses and so on. So and in fact correct some of the original mistakes of that people were making in relativity. And then Vera Rubin, who was an observer, astrophysicist, and made a major contribution to discovery of the dark matter, which again is another interesting story by itself in cosmology. Okay, any question there? So why did I tell you all about gravity? And why? Well, we got to the expansion, but now I want to, using the fact that I know the universe expanding, move that knowledge and go backward in time and see what would happen in the beginning. So universe is vast, and as far as we know, it could be infinite. So I have no idea how large it could be, but I know how much of it I can observe, and I know it's expanding. So if I take all of that together and put it together, let's say I take a piece of the space today, and I know things inside it are expanding, and then play the movie backward to see what happened in the beginning, then I know, well, let's say I have two galaxies today in some distance, and I put it as a unit of distance for myself to be 1. And then I go backward. This piece of universe would have been smaller. At some point, it would be half of its size today. We usually used to use some other way of quantifying it. We call it redshift, because lights also get redshifted as the universe expands. The frequency goes down, and
Yeah,
the
we can use the
wavelength of
redshift to find out how far away an
exactly.
object is, because also we would need to know how hot the star is if we wanted to find out how far away it is, because how hot the star is, its temperature, does greatly affect its color.
That's one way to measure
Hotter
distances.
stars glow bluer.
In fact, there's some of the best way to measure distances are based on what we call the standard candles. Standard candle is like a candle. You take it, the further away the candle is, the smaller it will look. So that's kind of what we do, but we have to have something that we know how it looks like in order to use that. And in this case, there are certain objects in astrophysics in space that do have a certain, we think we know how their light is. And for example, some kind of supernovae might be that. And we use that in cosmology to measure distances. And just a side note, another interesting thing that has become available to us very recently, this one is your age, the discovery, it's called black holes themselves. When stellar black holes merge, they emit gravitational waves. And those also we can use to measure distances, which is a very new thing and exciting thing. But let's get back here. So I'm moving backward in time. So my piece of universe is getting smaller and smaller. But can you get, if I'm like getting things more clump up and clump up, what else might be happening? Do you think it gets colder or hotter?
Hotter.
Rex?
Also,
Hotter.
your density is increasing. And what I wonder is, how come a black hole with the mass of the observable universe would have would have a radius of 13.8 billion light years, but how come the full universe which is like way bigger than the observable universe? At least as far as we know, it's larger.
Because we haven't observed the edges.
It was all compressed into a tiny space the size of a marble before the Big Bang. How?
That's a good question. So, because as you're pointing out, you go further and further back, it gets more clumpy and clumpy, it gets hotter and hotter and hotter. For one thing for sure, we know the elements cannot stay neutral anymore. They become ionized. And then at some point, even the nucleus breaks down. So things become like a very hot soup of mixture of we don't even have the heavy elements that we have today. It would be mostly hydrogen and ionized hydrogen and so on. So this is a part of the picture we can easily kind of understand what's happening. But as you were saying, if I move this further back, then it's going to be like it's not just a black hole. I mean, the whole thing breaks down. I don't know how to describe it. Do I? Yeah, because this, not only, first of all, not this, the rest of the space, the same thing happening to it. So I'm going to call this era Big Bang, and whatever before is a very interesting question mark that we like to understand. And in fact, I do spend a lot of my time working on that. It could be that, obviously, I know, as you were pointing out, if I push it too much further back, things can blow up. And I don't know if I have an image of, no. Yeah, I'm going back more forward, but because I want to make another
Wait.
point. But yeah, we don't know what's the before that in order to tell you that there's a black hole or not.
All the atoms in the universe formed during the Big Bang. All matter supposedly formed during the Big Bang. So the protons, electrons, and neutrons, technically, those can be directly converted into energy. They can't just be split apart. They can be actually destroyed.
Yeah, but there is
into energy, because nuclear weapons do that. Nuclear weapons do convert a very small amount of matter into pure energy. So every nuclear bomb that we set off, we decrease the amount of matter in the universe. Was that just happening in reverse during the Big Bang? Was energy becoming matter instead of the matter becoming energy? Was that what happened?
Hold that thought for one. Hold that thought. Okay, I'm gonna get into it a little bit in 1 minute. Okay, hold it, and then we get to it. So, because before that, I want to tell you about the age of the universe. So you might have heard that universe is around 14 billion years. And I want to say that's because we know the story up to that time. So from that one time, I can move the movie again forward and calculate how long it's been since that time where I had that hot soup of elements mixed up. Now, which is what we do today. There is obviously some complication here, like how much of like radiation I have, how much of neutrons I like, neutrinos and other things I have. But roughly, that's a calculated thing that we can do. But what happened before, that's something that is ongoing research. Now, let's get to your question, whether we had a nuclear bomb or not. So at that point, when you have like all the elements are, well, you only have hydrogen basically, because the other heavy elements could not form and could not stay stable in that high temperature. But there is a lot of conversion between electrons and protons and also into photons. So there is like interaction between these two. Jace, you have a question?
Yeah, can you go back to the last slide, please? The one right before. Yeah, thanks. No, the one after this one. Yeah, this one. So you mentioned that the universe was expanding faster. Yeah, right when we said this. So 9 billion years, the universe expanded by double, right? Because I'm assuming that the A means like basically like relative. So the A equals 1 means that's how big it is today. And when it says 0.5, that was half the size, right? So yeah, so 9 billion years it doubled. And then before that, I was expecting it to be slower. So in 3 billion years, so from 2 to 5 billion years, it went from 0.25 to 0.5. That seems like is actually faster than in 9 years it goes by 0.5 instead of by 0.25.
So you are doing this by how you're saying. So you're saying the doubling time is getting slower. Let me do the math. So the doubling time here is 3 billion years, and the doubling time here is wait, it's a little more, right?
Yeah, it goes by 0.25 in 3 years, and then here it goes, and it takes 9 years for it to go by 0.5.
Exact. So it has a slowed down. That's your
Yeah,
question.
slowed
That's your
down.
point. Yeah.
Under.
Yes. Yes. So it is true. Which is because it's most of this era is dominated by like I want to say ordinary matter, but not ordinary matter, by visible matter and dark matter. So it was starting to slow down. It's very, very recently. And it's that's why it was very hard. It was just recently discovered that you saw that it's because for acceleration to take place and the speed of things, it takes a little bit of a time. Well, in cosmology, a little bit is billions of years, but you are right. It overall, it looks like from here to here, it was a slower. I would have to, yeah, I wouldn't be able to do it on top of my head to tell you like how much of a small acceleration would change this. And in fact, it is a very small, but it is, yeah, measured.
Thank you.
I guess, no problem.
Wait,
I wish I had one of those pictures which had that. Oh, maybe I do have it. I can jump ahead. Let's see. I can show you here. So this is kind of the picture, as you can see. So this is time going forward. This is one of our satellites, WMAP, which 2003 was the data was released. So think of the radius, this circle being the universe now expanding. And as you see, it's kind of like it wasn't getting very fast. It has some acceleration. So it was over here at earlier time where matter and radiation were the dominant content of the universe. It was getting slower, but it starts to pick up a little bit around here. But it's a very subtle change. And I guess Erica, was it, who asked about what happened before, and did we have like a black hole, or what we call it is not in fact black hole, we call it Big Bang singularity. Did we have a singularity or not? That's a very active field of research.
wait. As we were saying before, would it be possible to convert energy into matter? We can convert matter into energy. So why can't we do it the other way around? You
We
can
could
store
do that,
an
yeah.
infinite amount of energy in a very tiny amount of space. And energy does warp space-time just like mass does.
So in fact, yeah, if you were in this region before, if you go even before hydrogen, there was at some point that even the hydrogen didn't exist. You have quarks. And then if you go further back, there is even time that even according to our theories of particle physics, they cannot hold up together. So this is true that at some point we think, and again, to be tested, because it's very hard to test the data. And this was part of what I wanted to tell you before the visible light can get to us. Let me get back to this later to you. Let's start with this era, because here is when I do have hydrogen, I do have photons, radiation, but it's so hot that you can see the light, even though it's interacting, hitting a lot of protons and electrons, it cannot get out. So it's kind of an opaque soup, plasma. But as we just said, universe expands. So this box expands, it cools down. And once it cools down, then the photons can travel freely in the space. And obviously hydrogen atom will form. And now the good news is, and this was again a next major discovery in cosmology, is that because the universe becomes transparent as soon as it cools down, there should be some remnants of the interaction and atomic, like the things that was happening again here, right? Because this light is coming. So we have this imprint of what was going on there just from that surface, just from this like boundary, that things, the photons started to come out. So this was something that physicists calculated and expected. They said, if our whole theories hold together, if this story of going back in time and getting to that era is correct, there should be these photons coming to us today. and we should be able to see them. In other words, again, this is another nice picture where you're looking in time. So we are sitting here. The galaxies have formed at some time earlier. But if you go further and further back, because everything gets hot and dense, a universe becomes opaque. But there is this surface, we call it the last scattering surface, but photons finally got freed. And they should, because now they're dealing with mostly empty space, we should be able to observe them today. And there should be this radiation from everywhere in the space, because I just took a piece of it, but it was from every piece. And when we are sitting on Earth or around Earth with our satellite, there should be a way to get some aspect of it. But they're coming from billion years ago, right? So, and the universe has expanded. And as we just said, the universe, the wavelengths get stretched out, which means the photons' energies go down. So they get cooler and cooler and cooler. So you have this radiation, you expect this noise coming from early time, but very, very small. It's very, very cold. And so this would have been a nice evidence for the Big Bang era. And turns out by accident.
Sorry, Jack has a question. Can we,
Oh,
Jack has
sure.
a question. He's been waiting patiently.
Oh,
Go ahead,
I
Jack.
didn't see that. And
No,
there are
that's
some things in the chat. Are they, I'm not monitoring
no,
the
it's
chat.
okay. It's okay.
Okay.
No, you don't have to worry about the chat. Go ahead, Jack.
Okay.
I've always wanted to know how and why did the Bang happen?
Can you say it again? How
and why did the Big Bang happen?
How and why? How did the Big Bang happen?
Yeah, how and why did Big
Oh,
Bang?
how and why, sorry. Yeah, I mean, some of it is that what I'm just telling you. It's just that because we think like the matter was clumped up and so hot, and so there was very hot. And maybe it's, sometimes people talk about explosion. It was an explosion in time. But what they really mean was, it was a very hot situation. The temperature was extremely hot and it was expanding. So if you call that an explosion, it is, I guess, in some sense, but it's not what I would picture an explosion, something exploding into something else. It was the whole space-time hot and expanding. So, and some people, when they say Big Bang, they mean that era and anything before. So also, that's also some of it. So now the evidence came nicely by surprise to these guys, Penzias and Wilson, who did not have intended to observe the evidence of the Big Bang. They were doing some kind of other observation with their dishes for radio astronomy. And they kept getting these noises in their satellites, some like random noise everywhere uniformly, very low temperature. And then I think they were in Bell Labs in Pennsylvania, and they checked with their friends in Princeton, theorists. Apparently, first they thought it could be the pigeon droppings, and they cleaned out the dishes to see if it goes away. But after it's persisted, and this is around 1978, I think. Turns out, no, they were actually observing the Big Bang. So it was the remnants of the Big Bang, those photons coming from every direction to us on Earth, and very uniformly with the temperatures of extremely cold temperature, 3 Kelvin. By the time they reach us after billions of years, that's how cold they are. And nicely, they got the Nobel. The Nobel was not in 2000. I think the Nobel was 1978. It is just picture was produced in 2015. But yeah, so it's always nice. One day you get some noise and then tomorrow you get a Nobel Prize for that. Right. But since then, their observation, in fact, was in 1962. The Nobel was 1978, in fact. We have made a lot of progress. So not only the discovery, this is actually called a cosmic microwave background. So not only we observed the minimal distribution of the cosmic microwave background, the satellites, the generation of the satellites that have come after have measured even like how slightly hotter or colder in each direction the photons are. And this is a very precision measurement in astrophysics. So think of it again, 3 Kelvin is almost like negative 300 Celsius, right? It's extremely cold, almost close to 0 Kelvin. Now, on top of that, which by itself is a very hard measurement, they're measuring ups and downs and slight fluctuations, which is 1 in a million on top of that 3 Kelvin. And as you can see, it has become so much better and better, higher resolution. And why do they do that? Because the information in these little dots tells us what happened before that era. Because again, remember I said the photoslip was opaque, then it became transparent and came to us. We want to know what happened before, to crack the box and see, like, was it, like a nuclear bomb, or was it a black hole or something else? And the key, we hope, that is imprinted in this. In some sense, a lot of information we have already extracted from this. Okay. Let me just put it all together. Yeah, so this is the mathematical language that people work with. This is, like, we call it like a power spectrum. You take them, use mathematical tools, take them to different space, like a Fourier space, and use engineering tools to measure them and analyze the statistics of that. And it's so nicely, for example, matches what we think it should match. So the dots are the measurements, and the blue line is the curve that cosmologists have predicted, and they fit so nicely together. So that's how good we have gotten with our mathematics and theories. Now, but that's not the whole story. As you can already see, I have holes in my story, things that I'm saying, well, there is this thing, I don't know that thing. So to give you in a nutshell where we are at, so we understand this surface, these photons, this green area, and all the dots coming to us. We kind of have probed things from then to us through the formation of galaxies. But one thing people have realized is that even the matter in this region, all the visible matter that we can estimate or measure, cannot quite account for the amount of the gravity that exists and the movement that exists, like the slowdown, or the how the object in galaxies rotates around their center. So there is some missing matter there for sure, which is we call them dark matter. So understanding the nature of dark matter is one of the biggest puzzles of cosmology today, and particle physics. The other one, as I pointed out, we don't see beyond this surface when the universe was opaque. And a lot of things could happen before that. So Big Bang, could be that universe was infinitely old, it continued forever in the past. It could be there was some major dramatic event, like a singularity. We came out of a different phase, the whole universe. A lot of things could happen there. And as I pointed out, there is this more recent puzzle that was added about a couple of decades ago, that it's acceleration. So again, gravity doesn't quite match, as we know, the Einstein gravity. We have to add the constant, but if we add it, is it quite the right one? There's some puzzles with that. And so there's a lot of also investment in understanding that part. I want to quickly wrap up. I know, just give you a couple of one picture and one video, and then again, open it up to any questions you have. One, again, perspective. In cosmology, things that are like yesterday, in fact, in the scale of things that we measure in history, are way, way longer in the past. Like if I put the whole the time from the Big Bang era to today, I fit it in 1 year calendar. Like the time that I said was January, and then the galaxies formed in February, and then know what's happening here in September. I think solar system was formed in September, and then like the rise of the dinosaur, for example, is only like 4 days before the end of the year. And then I think we would be just like our existence would be just before the midnight. I think it was a few seconds or so. If I don't know if I have it. Yeah. So on December 31st, most of our history, human history, or even animal history, has happened on the last day of the year. So how that's the perspective of a cosmic history versus the human history. And one other thing I wanted to show you is a very recent video of a snapshot of the universe. Do you hear the sound, or does the sound come through? No.
I don't hear anything.
Okay, that's fine. The sound is just a music, but
Why do
so
I
this one,
all the time?
so this is based on actual observation, this reconstruction. And these are the actual galaxies that have been observed.
Why do I constantly have to be muted? Why do I have to always be muted? I don't like not being able to talk. I just don't like it. Thank you.
So, yeah, that's the last, just to give you one, let's see if it shows it. Oh, no. Yeah, so it doesn't put the, yeah. Okay, yeah, so this here, as you can see, there is like in the middle is the ones, galaxies that we have observed, and the structure, which is kind of similar to what I mentioned in the beginning from the simulation, like these patterns, which also that you were asking. So these are actually observed.
Can I tell you a fact about that thing? There's like, you see that it looks kind of like butterfly wings. Like there's like two things.
Do you know now
Those
why?
blank parts are the parts that we haven't observed yet.
Do you know why we cannot observe those parts?
No, why?
Any idea? I think, and again, I'm not an observer. I feel like because so we have two good views towards the space, and those are the out towards the galaxy plane, because galaxy kind of blocks our view if you look into its own plane. So a galaxy is kind of like a disk. And my guess is the cones are the ones, so we can see very well if you're looking outwards the galaxy. So those cones are best viewed, but then things that are like in towards the plane of the galaxy gets blurred out, and so they cannot reconstruct it or completely understand. Like there's a lot of stars that blur the telescope, and
Or
so
maybe
that's harder.
Or maybe people are so interested on those two sides that they haven't thought of doing the middle parts.
That could be, yeah. But I think that's pretty much right. Like, so there's all of these complications that things can block our telescopes. And there is like other interesting stories like with observation. For example, some of the best locations to make observations are either on South Pole on Earth. Can you guess why that is?
Because
Alexander?
what?
Sander, is it Alex? Go ahead. Why? You're mute.
Because of the magnetic poles.
Not quite. It's because South Pole is one of the driest places on Earth. And the other one is in Chile, like on the mountains. So dry places are very good for observation. The humidity kind of blurs the view of the telescopes too. Okay, that was my talk. So I'm happy to answer other questions and anything else.
But are we at the center of that butterfly? Is that viewed from
Yes,
our point of view? Okay.
exactly. Yeah. So I don't know how to pause it and keep it there,
But there is
let's
no, so there's no view. There's a certain region of the space that is blocked, or that's the way that we are just observing. Like that's how
yes.
you're pointing.
So let me, yeah,
sorry.
so let me see if I can. So if we are here, I'm gonna zoom it out, then our galaxy is kind of like this.
Oh, okay. Oh, so
Obviously
maybe
much
I see.
smaller.
So it's probably harder to see through the galaxy. Is that right?
Exactly. Yeah, that's why we cannot see in these directions,
there
because
you
it's
go.
blocked by the galaxy itself. But out towards the outside of the galaxy,
There
then
you
it's there is much easier to observe things.
Okay, yeah, that makes sense. All right, thank you.
Mhm.
So August, do you have a question?
Okay,
Thank you. Bye.
do we know?
Bye, take care.
All right,
Go ahead,
thanks.
August.
Yeah, thank you so much. If anybody else have a question, now's the time to ask.
Do we know what's gonna happen when everything spreads apart? Like like when everything gets as far apart, like as you can't see anything, like maybe even as far apart, maybe like far apart from our sun.
Could I?
Yeah. Did you want to answer that, Rex?
Oh, sure. Well, that's actually one of the possible scenarios for the ends of the universe. The Big Freeze, also known as heat death. It's when
I know I've watched that same video. I was trying to explain it in a more like friendly, like not scary to all the other kids.
Yeah, it's not as scary at all, first of all, because if it happens, it's gonna be billions of billions. I don't know if even like not only us, the Earth would like, but then it's way beyond our life. So don't worry about that.
It seems like that's what's going to happen, but there's a silver lining. Heat death. It takes the longest to kill the universe. So yeah, so you have more time to spread to other galaxies or play Super Mario Bros. Or something.
Yeah, but it is true that if the universe, if we have like this dark energy persist, then things get further and further away, and there will be a time that obviously I won't exist here, or I'm not sure even Earth or Sun would be here anymore, but the galaxies would not see each other's light anymore, because that's how far away. They won't even, like, the light can never get to the other ones because of the way that the universe gets curved up, like so fast and so quickly accelerating, getting away from each other.
There was one more question. I think it was, who was it? I can't see anymore. Oh, okay, Torin, you go. This is the last question because we have to respect Professor Gheshnizjanni's time also. Let's just ask one more question and then we let her go. And we thank her and then we let her go. Torin, go ahead.
When will the Andromeda and Milky Way galaxy collide?
Are they going to collide? I don't know. Yeah, I'm not sure actually they're gonna collide, but you know what? It's a little bit outside of my expertise.
They are.
Oh, okay. Good to know. Thank you for telling
In
me.
4.5 billion years, they're gonna collide.
It
There we
knows.
go.
Okay, very
That's
good.
nice.
All right, good job, everybody. All right, let's thank Professor. Sorry, let's thank Professor Gheshnizjanni. She came all the way from from Canada through Zoom.
Yes.
So
Yeah.
thank you so much for your time, and thank you for giving us a talk and answering the
Thank-
questions and the
Thank
kids
you.
too.
Thank you.
Thank
Thank
you.
you for
Thank you so
joining.
much. It was a great talk.
And I had
Thank
fun
you.
talking to you all, and have a nice time. And I hope to see you one day in my office, and yeah, as colleagues. Okay.
Thank you.
Take care.
Thank you so
Thank
much.
you.
Have a good
Bye.
day.
Stop the recording.
Thank you.
Thank you so